Slide 1. This program is the second in a series of presentations on electrophysiology of the heart, prepared by the American Physiological Society. 2. This slide tape is part 2 of Basic Membrane Physiology. Content expert, Dr. Harry Fozzard. 3. The program consists of an entry skills test, narrated development of the subject with accompanying visuals, and a post-test. Stop the tape to answer questions and to check answers, which will appear during the subject development as well as in the entry skills test and post-test. 4. Now stop the tape for the first question of the entry skills test. 5. 6. 7. 8. 9. 10. The following topics will be discussed. First, Ohm's law in terms of conductances and ionic driving forces. Second, the voltage clamp technique. Third, the variation of sodium and potassium currents and conductances with time and voltage. Fourth, the ionic mechanisms for the three phases of the action potential. Fifth, the role of the sodium-potassium pump. 11. Your first objective is to express Ohm's law in terms of conductances and ionic driving forces so that changes in ionic currents and membrane permeability can be quantitated. 12. The relationships between an ionic current and its determinants can be understood in terms of Ohm's law, which states that the potential difference measured as voltage, V, is equal to the product of current, I, and resistance, R. The factors in this equation can be rearranged to show that current is equal to voltage divided by resistance. Conductance, G, the reciprocal of resistance, is a more useful term for our purpose, since it indicates the ease with which each ion can cross the membrane. Substituting the conductance factor for the resistance factor, we now have current equal to conductance times voltage. 13. The ionic current for a specific ion, I sub I, is equal to the product of the membrane conductance of the ion, G sub I, and the voltage acting on that ion, V. This voltage, V, is equal to the electrochemical equilibrium potential for the ion, E sub I, minus the membrane voltage, V sub M. Substituting the factors in the first equation results in I sub I equal to G sub I times E sub I minus V sub M. 14. The equation stated in this way identifies the factors of the driving force on the ion, E sub I and V sub M. 15. Consider the value of the current when there is no driving force on the ion. When the voltage across the membrane, V sub M, equals the equilibrium potential, E sub I minus V sub M is equal to 0. Consequently, V, the driving force, is equal to 0. No current will flow under these circumstances, even though the membrane conductance can be very large. 16. When the driving force on the ion is equal to 0 and no current flows, depolarization of the membrane stops. 17. 18. 19. As your second objective, you should be able to describe the voltage clamp technique and state its use in 1. Measuring the dependence of sodium and potassium current on voltage and time, and 2. Calculating sodium and potassium conductance. 20. Conductance, G sub I, can be calculated if the ionic current, I sub I, the equilibrium potential, E sub I, and the membrane voltage, V sub M, are measured. If we suspect that a change in membrane conductance to sodium, GNA, is responsible for the action potential, we would like to calculate the way in which sodium conductance changes as a result of depolarization. 21. During the action potential, voltage and current change simultaneously. In order to calculate conductance, one of these two parameters must be held constant. The voltage clamp technique is a means by which the voltage across the membrane of a cell can be controlled. Using the relationship presented in the previous slide, G sub I equal to I sub I divided by E sub I minus V sub M, we can calculate the way in which ionic conductance depends upon membrane voltage and time. 22. In the voltage clamp technique, two electrodes are introduced into a squid nerve fiber 0.5 to 1 millimeter in diameter, which is immersed in seawater. One electrode records membrane voltage and the other injects current from a feedback amplifier. 23. The recorded membrane voltage is fed into an amplifier which compares this voltage against the clamped or command voltage and generates current proportional to any deviation in the membrane voltage. The applied current flows through the membrane and is either increased or decreased to make the voltage across the membrane equal to the command voltage. 24. Such an experiment gives the following results. A squid nerve has resting potential of minus 60 millivolts. A current from the electrode is applied at the time indicated by the arrow. This current changes the voltage on the capacity of the membrane from minus 60 to minus 30 millivolts. 25. Then, a small inward current through the voltage clamp holds the membrane voltage at minus 30 millivolts, offsetting a small outward ionic current. This current would be maintained as long as the voltage step lasts, unless the membrane conductance changes. 26. However, after a short time, the feedback amplifier must provide a large transient outward current in order to continue to hold the membrane at minus 30 millivolts. 27. This applied current is equal and opposite to the ionic current crossing the membrane. The applied outward current offsets a tendency of the fiber to depolarize and is a reflection of a transient inward ionic current through the cell membrane. If the voltage clamp was not applied, the inward ionic current generated by the membrane would depolarize it beyond the clamped potential of minus 30 millivolts. 28. We can determine what part of the current is due to the movement of sodium ions by making the voltage step with sodium removed from the solution bathing the nerve fiber and comparing this current with that of the similar experiment in which sodium was present. 29. The difference in current with sodium and without sodium is a measure of the current that the voltage clamp must supply in order to offset the transient sodium current that results from entry of sodium into the cell. 30. With the voltage step, the sodium current rises to a peak after about 1 millisecond and falls back to a low value. 31. If we assume that total membrane current is made up only of sodium and potassium current, a reasonable assumption for the squid nerve, then the current remaining after sodium ion removal is a measure of the current that the voltage clamp must supply in order to offset potassium entry. 32. During clamped depolarization, the measurement of the ionic current as it varies with voltage and time makes it possible to determine changes in ionic conductance. For example, we know the equilibrium potential for sodium, ENA. If we set the membrane voltage at a chosen value, ENA minus V sub m for that value becomes a constant K. From the experimental curve, values can be selected for the sodium current as it varies at different times. The sodium conductance, GNA, can then be calculated for each value and the resulting conductance curves plotted. 33. 34. 35. 36. 37. Your third objective is to contrast the time courses of sodium and potassium current and conductance when the membrane is depolarized and held by the voltage clamp. 38. As we have seen, the voltage clamp technique makes it possible to measure the amplitude of the sodium current, I, and the time course of that current at a particular voltage. Therefore, we can obtain a family of curves reflecting the course of the sodium current at different command voltages. Note that voltages of minus 40 and minus 50 millivolts are close to threshold and therefore generate currents of low amplitude. Note also that there is less driving force and therefore less current flow at V sub m equals 0 than at V sub m equals minus 20 millivolts. That is, when V sub m equals 0, the voltage difference across the membrane has been abolished, and the only factor favoring sodium movement is its concentration difference. 39. Knowing the current and the driving force, the corresponding time course of sodium conductance at each clamped voltage can be calculated. Even though peak sodium current is less at V sub m equals 0 than it is at minus 20 millivolts, the calculated sodium conductance at V sub m equals 0 is larger. Remember that current is a product of conductance and driving force, and that as the membrane is depolarized, the driving force decreases even though the conductance increases. 40. A comparable family of curves for potassium current is illustrated. Note that the time scale has changed, and that potassium current rises to a new level which is maintained. The driving force always increases with increasing depolarization, so that the current is always larger. 41. A family of curves showing potassium conductance can be calculated. Note that conductance of potassium rises faster with greater depolarization. 42. The sodium current and conductance rise rapidly with depolarization beyond threshold and then fall. Potassium current and conductance rise slowly with depolarization. Definite mathematical functions have been derived to describe the dependence of sodium and potassium conductance on membrane voltage and time, but the derivation is too time-consuming for this lesson. 43. 44. 45. As your last objective, you should be able to 1. List the three phases of the nerve action potential and identify the ionic mechanism for each. And 2. State the role of the sodium-potassium pump in a single action potential and in maintaining ionic gradients in steady-state conditions. 46. Let us consider the ionic mechanisms responsible for the three phases of the action potential: depolarization, overshoot, and repolarization, using our knowledge of the way in which sodium and potassium conductance depend on voltage and time. 47. If we depolarize to threshold, we permit a small increase in sodium conductance. Some sodium ions enter the cell down the electrochemical gradient. This entry of positive charges depolarizes the cell membrane at that point even more, leading to a further increase in sodium conductance and an increase in sodium entry. This positive feedback feature is why the action potential is called regenerative. 48. What halts the depolarization during the overshoot? As sodium conductance increases more, the entry of sodium ions brings the membrane potential closer to the equilibrium potential for sodium, ENA. As V sub m approaches ENA, the driving force, V, is equal to 0. There is no current flow because there is no potential to move the ions. Further, the rise in sodium conductance is transient, so that by the time the membrane is depolarized near the equilibrium potential for sodium, the sodium conductance has already begun to be turned off. 49. How does the cell repolarize? With more time, the transient rise in sodium conductance has been effectively turned off. In addition, the slow rise in potassium conductance with depolarization becomes apparent. This fall in sodium conductance and rise in potassium conductance causes the membrane to return to its resting level near the potassium equilibrium potential. After repolarization, potassium conductance returns slowly to its resting value. 50. The ionic gradients needed to provide the driving forces on the ions are established by the sodium-potassium pump, which maintains a high concentration of potassium inside the cell and a high concentration of sodium outside the cell. 51. However, the pump plays no role in a single action potential. With each action potential, a little sodium enters the cell and a little potassium leaves the cell. Over the long run, the pump must restore the ionic gradients. But the reserve is so large that if the pump is completely blocked, a nerve may develop as many as 10,000 action potentials before it accumulates enough sodium to make it inexcitable. 52. 53. 54. 55. 56. In summary, we have discussed a rearrangement of Ohm's law which allows the calculation of ionic conductance from experimentally derived data. A short and simplified discussion of the voltage clamp technique, which is used to determine the voltage across the membrane and to measure current flowing through the membrane, has been presented. 57. Since the voltage clamp supplies current to offset membrane ionic currents, it provides a record of the ionic current. This can be divided into sodium current and potassium current by measuring the currents before and after removal of all the sodium ion from the solutions. By analysis of these currents, the dependence of sodium and potassium conductances on time and voltage could be determined. This knowledge was then used to identify the ionic mechanisms responsible for these phases of the action potential. The role of the sodium-potassium pump in long-term maintenance of the cellular ionic gradients was mentioned. 58. Now take the post-test. 59. 60. 61. 62. 63, 64, 65, 66, 67. This concludes our discussion of basic membrane physiology.